In the next section, we'll look at what exactly the equilibrium constant means and how we can work with it mathematically. So firstly, let's just talk about the meaning of KEQ, so our equilibrium constant. What does it actually tell us about the reaction? Well, in general, it tells us how far a reaction will proceed. And it gives us an idea about how much the forward reaction is favored or how much the reverse reaction is favored. So if we remember that KEQ is equal to the concentration of the products over the concentration of the reactants, and we start to think about that mathematically, we can think about what the value of KEQ actually tells us. So if we had a very large value of KEQ, what would have to be mathematically true in order to have a large K value? That would mean that our numerator, the top part of our fraction, would have to be very large. Meaning, our forward reaction would be dominant, meaning we have lots and lots of products. So if we have a K value much, much bigger than 1, it tells us that the forward reaction is favored, or in other words, that the products are favored. So it tells us that we have more products than we do reactants. So even though we're still at equilibrium, and we still have reactants and products being formed, the reaction will favor the product side. So the products will be greater in concentration than the reactants. But if we think about KEQ being small, so what does it mean if we have a small K value? Mathematically, what has to be true? Mathematically, that means the denominator needs to be much greater than the numerator. In other words, our products must be favored. I'm sorry, our reactants must be favored, not our products. Okay, so our denominator, remember, is our reactants. So that means our reactants must be favored. Okay, so if K is much, much smaller than 1, then our reverse reaction is favored. Okay, so we have a higher concentration of reactants than we do products. In other words, the reaction does not proceed very far in the forward direction. So maybe it's a slow reaction or a non-energetically favored reaction. For whatever reason, it lies more on the reactant side than the product side. Whereas again, if we have a large K value, it favors the product side. So one way we can manipulate the equilibrium constant, so suppose instead of looking at the forward reaction, we were looking at the reverse reaction. Because remember, we can always look at any equilibrium reaction from either side. So if I reverse the chemical equation, I need to invert the equilibrium constant. In other words, take 1 over the equilibrium constant. So Kr, the reverse equilibrium constant, will be equal to 1 over the equilibrium constant of the forward reaction. Okay, so if we take a look at N2O4 is in equilibrium with NO2, our Kc value for the normal forward reaction would be the products of the reactants, so NO2 over N2O4, and NO2 is squared, and we have a value of 0.212. This is at 100 degrees C. So what happens if we want to reverse the equation? So now we have NO2 giving us N2O4. So now my Kc value is the opposite. So now I have my products N2O4 over my reactants NO2 squared. So now if I want to know what the Kc value is, I can just take 1 over the forward reaction K value, and that gives me 4.72 at the same temperature. So just 1 over the Kc value for the forward reaction gives me the Kc value of the reverse reaction. So that's our first manipulation. So we're going to go through a few of these. First one is reversing the reaction. Okay, what if instead I want to multiply the reaction by a stoichiometric coefficient? Okay, so suppose I'm manipulating the equations, trying to add together elementary equations to get one main equation, or overall equation. Suppose I need to multiply by a stoichiometric coefficient. If I do this, I'm going to raise the equilibrium constant by the same factor. So if I multiply the reaction times 2, or by 1/2, I would raise my Kc value by the same thing. So here, what if we multiply the equation by 2? So now instead of having 1 N2O4 giving us 2 NO2, we have 2 N2O4 giving us 4 NO2. What do we do with the Kc value? Well, now we want to square it. Since we multiplied by 2, we'll just square our Kc value, and that will give us our new Kc value. So whatever we do to our equation, we raise our Kc value to that same power. So even if we divided by 2, you could raise it to the power of 1/2. What if we add 2 or more chemical equations? What do we do with the Kc then? So if we add more than 1 or more chemical equations, we'll multiply the Kc value by each other. So if we have more than one Kc equilibrium constant, and we add those 2 equations together, we multiply them by each other. Okay, so for example, here we have silver chloride giving us silver plus and Cl minus, and we have a second equation, silver plus 2 ammonia, give us AgNH3 2, and that's aqueous. Okay, so if we add these together, we get silver chloride plus ammonia, give us AgNH3 plus Cl minus. So we've added them together. So what should we do with our K values? Well, we have a K1 and a K2 for each equation. So if we want to know the net K value, we'll just multiply them together. Okay, so K1 times K2 give us the new value. Now you can kind of see mathematically what we're doing. Okay, but the new K value will just be the first K value times the second K value. Okay, we don't really care about the numbers at this point, but 2.9, this would give you a new K value of 2.9 times 10 to the minus 3. Important thing here is understanding that if I want to know the net K value, I need to multiply them. Okay, so here's one for you to try. It says a mix of nitrogen, hydrogen, ammonia gases are brought to equilibrium when the equilibrium equation is written using whole number coefficients as follows. The value of Kc is 3.5 times 10 to the 8th. It says, however, the equilibrium can also be written as, and they give you a second equilibrium, they want to know what is the value of K2, and then they give you a third equation, and they want to know what is the value of K3. Okay, so it's just a rearrangement of that same equation. Okay, so give this one a try. This should not be overly difficult, and let's see what you come up with. Okay, so let's look at the first one. So let's see, what have they done? So they've gone from nitrogen plus 3 hydrogen give us 2 ammonia. And our new equation is 1/2 nitrogen gives us 3/2 hydrogen, which is in equilibrium with ammonia. So we want to know what is K2. So what they've actually done to this equation is they've divided everything by 2. So 1/2, 3/2, and 2/2, which gives us 1. Okay, so to get our new K value, K2 will be equal to K1 raised to the same power as what we just multiplied by the equation by. Okay, so we just raised K1 to 1/2. In other words, take the square root either way. So it would be 3.5 times 10 to the 8th raised to the 1/2. Okay, which gives you a new K value of 1.9 times 10 to the 4th. Okay, so now looking at between K1 and K3, so looking at these 2 equations, let's take a look at what they've done. So the first one, nitrogen plus hydrogen give us ammonia. Now we have ammonia giving us nitrogen and hydrogen. So we reverse the equations. So what do we do to our K value? We take 1 over the K value. So K3 will be equal to 1 over K1. So it'll be equal to 1 over 3.5 times 10 to the 8th, which gives you 2.9 times 10 to the minus 9. Okay, so just make sure you know the rules on what to do to manipulate the equations and the K values, and these should be a piece of cake. Okay, so now here's one where we need to actually come up with a new equation. So they've given us our third equation, and they've given us 3 equations that make it up. So what we need to do is figure out how to manipulate these equations to get to our final equation. So the following equilibrium constants are given at 500K, and it wants to know what is the KEQ value for the 4th equation. So they give us K1, K2, and K3. So what you need to do is figure out how to manipulate these equations so that when you add them together, they give you this final equation. Okay, so remember our rules. So remember you can multiply by something, divide by something, you can reverse the reaction. And then when you add them together, remember that you'll multiply the K values. Okay, so see what you come up with for this one. Okay, so let's take a look at our equations. So first, let's look at the target equation. Okay, so we have hydrogen by itself, so not H2, just H, plus bromine, and again, not bromine gas, just Br, gives us HBr. Okay, so if we take a look at our equations, we want to see where can we get these different building blocks from. So where can we find H by itself? The only place we can find it is here. And where can we find bromine by itself? Again, the only place we can find it is in this equation. Okay, so what can we do so that we end up with bromine and hydrogen by themselves on the left-hand side of the equation? Okay, so we need to inverse this equation and this equation. So in other words, reverse them. Let's say reverse, not invert. That kind of doesn't sound right. Let's say reverse. Okay, and what about the first equation? Well, if we look at our product, HBr, this already has the product HBr on the right-hand side. Okay, so we can leave this one alone. So our first one we'll keep just as it is. Okay, so we don't need to do anything here. And our second one, we said we would reverse it. So remember, when we reverse the equation, we take 1 over our K value. Okay, so we come up with a new K value. Our third one, we also reversed it. So again, 1 over the K value, so we have a new K value. Okay, now we can cross out anything that appears on both sides of the arrows. So H2 will cancel with H2. Bromine will cancel with bromine. And now we can add these together. So we end up with 2H plus 2Br gives us 2HBr. And to find this K total, now we need to multiply 7.9 times 10 to the 11th times 2.1 times 10 to the 40th times 4.5 times 10 to the 14th. In other words, multiply all your K values by each other. So KT is equal to K1 times K2 prime times K3 prime, which gives you 7.5 times 10 to the 66th. But we're not finished, because if you notice, this equation is 2 times the equation that we actually need. So we have 2's here, and we don't need them. We just need 1's. So we can divide by 2. So divide the whole thing by 2. So here we divided by 2. So what do we do with our K value? So now, with our K value, we also will divide by 2. So in other words, we're multiplying. I think a better way of thinking of this, because that's going to confuse you, is just to say times 1/2. So 1/2 times 2 gives you 1. So what do we do to our K value? We also raise it to 1/2. In other words, we take the square root. Raising to 1/2 and taking the square root are exactly the same mathematical idea. Okay? So we end up raising 7.5 times 10 to the 66th to the 1/2 power, in other words, taking the square root. So you end up with a new KEQ, 2.7 times 10 to the 33rd power. Okay, so just by manipulating the equations to get our new final equation, and knowing what to do with the K values, we can figure out the KEQ for the new reaction. In the next section, we'll talk about heterogeneous equilibrium. So far, we've really only been talking about homogeneous equilibrium. But what happens when we have something that's in a different phase? So what exactly is heterogeneous equilibrium? So this is this is equilibria for reactions that have pure liquids or solid as reactants or products. So 2 things make an equilibrium heterogeneous. So outside of having aqueous things that are in solution, if we have pure liquids, things like H2O with an L, a liquid, or solids as reactants or products, then we have a heterogeneous equilibrium. And we say that concentration is a property that only applies to mixtures and not to pure substances. So as long as the pure liquid or solid species are present in excess, they have a constant concentration. In other words, their concentration doesn't change. Okay. So we have an example here of carbon monoxide, giving us CO2 and solid carbon. And this is an equilibrium. Okay, so it says this equilibrium is not dependent on how much solid carbon is present, as long as there is some carbon present. So we have two containers, both with some amount of solid carbon, and both with a mixture of CO2 and carbon monoxide. So we have our equilibrium, CO giving us CO2 and carbon. In other words, it's depositing carbon onto the ground and giving off CO2. And then we have carbon recombining with CO2 to give us carbon monoxide. So as long as we have some carbon present, doesn't matter exactly how much, as long as we have it present in excess, then we're going to consider its concentration to stay the same. So whether we have a lot of it or a little of it, we'll consider it to be the same concentration. And what this tells us is that we don't include it into our equilibrium constant. So the concentration of solids and liquids do not appear in the equilibrium expression. So if I write the equilibrium expression for carbon monoxide, giving us CO2 and carbon, notice what's missing. So my product side, there's no times the concentration of carbon solid. So in other words, this isn't affecting our equilibrium in any way. As long as it's present in excess, we'll consider it to stay constant. So therefore, it's not a part of our equilibrium expression because its concentration isn't changing. Since we can only measure concentrations for things like aqueous solutions, we can't measure concentration for something like solid carbon. So we do not include it in our equilibrium expression. Okay, so here's a couple for us to try together. Okay, so it's just a series of equations, and they want us to write Kc or Kp, and for the case of gases, you can write both. So our first one, we have CO2 plus carbon gives us 2CO. So take a second and try to write your K expression for this equation. Okay, so we'll write our products over our reactants, and we'll come up with, for our Kc value, CO squared. CO because we have squared because we have this 2 up front. Okay, and that's going to be over our reactants, which will just be CO2. So we're going to forget about solid carbon here, because remember we said solids are not included. And same thing for our Kp. So now we'll say the pressure of CO squared over the pressure of CO2. Okay, the next one, we have mercury liquid plus aqueous mercury ion, giving us Hd2, 2+, also aqueous. So see if you can come up with a Kc expression for this. Okay, so again, we'll do our products over our reactants, and then we'll have to see if there are any reactants we can forget about, or products we can forget about. Obviously, everything on the product side is aqueous, so nothing we can forget there, so we have to include everything. On the reactant side, we see a pure liquid, so we can forget about that. So our Kc will just be Hg2, 2+, over Hg 2+. So products over reactants. Next one, so here we have copper hydroxide, giving us aqueous copper ion and OH2-. Okay, so first let's see if there's anything on the product side we can omit. Aqueous ion, no. Okay, but on our reactant side, we just have solid copper hydroxide. So we can omit this whole thing. So our Kc expression just becomes Kc is equal to the concentration of our product, so copper ion times hydroxide ion over 1. In other words, Kc is just equal to copper ion times hydroxide ion squared. Okay, one more. So here I have tin oxide, and that's a solid, plus CO gas, giving me tin solid and CO2. Okay, so let's see if there's anything we can forget or anything we can omit. Okay, on our reactant side, we have tin oxide, that's a solid, and our product side, we have tin solid. Okay, so our Kc expression will just become CO2 gas squared, so that's our products, over carbon monoxide squared. Okay, that's our reactants. And we can also write Kp. So it'll just be the pressure of CO2 squared over the pressure of CO squared. Okay, next one, calcium carbonate solid, giving us calcium oxide solid and CO2 gas. Okay, so we can omit copper oxide solid and copper carbonate solid. So our Kc just becomes products over reactants, just like always, but our only product now is CO2. And it's also a gas, so we can write Kp is equal to the pressure of CO2. Okay, next one. So we have zinc solid plus copper ion, giving us copper solid and zinc ion. So a nice redox equation. Okay, so we can omit zinc solid, we can omit copper solid. So our Kc expression is just zinc ion over copper ion. Okay, now we have iron 3 plus OH minus gives us iron hydroxide. Since iron hydroxide is a solid, we can omit that from our equilibrium expression. It's not included. So our Kc value becomes 1 over. Okay, so we still have to put a 1 there because we don't have any products, but it'd be 1 over iron ion times OH ion squared, or cubed, excuse me. Okay. So in the next section, we'll move on to calculating equilibrium constants, and this is where we'll start to get into some ice tables, so I want to go ahead and make a break in this section.